Okay, so this is chapter 2. I have not started recording yet. Chapter 2 really has to do with the chemistry. And so most, if not all, this should be a review. It's water-based chemistry since we are water-based organisms, most of us are. I knew a few people in college that seemed to be luscious and be based off of alcohol. Okay, please note that was a secular university, not that. Alright, so you're recording this. Alright. Remember, the number one thing about water is the fact that it's polar. It has a very high dielectric constant, which just has to do with how polar it is. Okay? And it can form hydrogen bonding. Now, one big thing that's different than the way, at least I taught Gen Chem. Let me bring this back down. Well, I'll forget about that. Trying to. And what I teach biochemistry is, remember in Gen Chem, you learn about hydrogen bonding. So water can do hydrogen bonding. And you learn for hydrogen bonding, each partner had to have both a hydrogen bond donor and acceptor. But in biochemistry, it's not black and white like that. There are shades of gray. You'll find out that there are, it would be a stronger hydrogen bonding if both partners have a hydrogen bond donor and acceptor, but they only require each one to have at least one. Okay, so that's why we have different degrees of hydrogen bonding in biochemistry. So just be prepared. Like if you all of a sudden see like an amide doing hydrogen bonding off of carbonyl carbon, and you're like, wait a minute. Oxygen, I should say, carbonyl oxygen. You say, but wait a minute. You know, in organic chemistry, and especially in Gen Chem, that would not be considered a hydrogen bond. It would be considered a polar bond. In biochemistry, that's considered a type of hydrogen bonding. Okay, but water is very polar. Water can do hydrogen bonding. You know, there's an overall dipole moment, which you see like that. Whoops, it's supposed to be a plus. So, therefore, that's the overriding property of water. All right. Electronegativity, you should already know about electronegativity. Fluorine is the most electronegative on the Pauling scale. We usually say carbon and hydrogen are about equal. They're not so different in order for them to be polar with respect to each other. They're approximately equal. Technically, hydrogen's a little bit less electronegative than carbon, but not enough for it to really make a big difference, okay? So, of course, naturally occurring biomolecules, we don't talk about fluorine. Fluorine would only be in drugs, okay? But yeah, you know, we don't have amino acids that have fluorine in them or anything like that. So the ones that we are talking about the most are these, you know, oxygen, nitrogen, sulfur, carbon, and hydrogen. Okay, we do talk, once in a while you'll hear, you know, magnesium is important in biochemistry and things like that as well, but we're very much more limited than you were in organic chemistry. Definitely much more limited than you were in Gen Chem. There's only a few players. Okay, for things that are naturally occurring. Now, obviously, if you're taking some type of xenobiotic, then, what does that mean, xenobiotic? Xeno means foreign, from the outside, you know, drugs or whatever, then you can have other elements that are really important. Selenium, you know, obviously trace metals are important too on here. Polar bonds. Okay, so we'll come here. The different types of bonding. Okay, and so here we're talking about non-covalent bonding. Okay, obviously a covalent bond is going to be stronger than those that are non-covalent under most circumstances. In vivo, it's not listed, but you can have ion bonding. It's just that water itself is not in an ionic form. Usually it's going to be hydronium and hydroxide together, so therefore in and of itself, it's not going to be just an ion. That's why they have it listed this way. But you can have ion-ion interactions. Okay, and so I would expect you to already know about ionic interactions, ionic compounds, the whole idea. Electrostatic just means, you know, a plus with a minus. Also, you can have like negative repulsion or positive repulsion, things like that. Okay, but for water in particular, we're talking about ion-dipole interactions, dipole-dipole, and then dipole-induced or van der Waals interactions with the actual dipole. Usually, these would be stronger. These would be the weakest. with respect to water. We are skipping the numbers. So just because of time. But you can see here how the take-home message here is that a covalent bond between oxygen and hydrogen is much more stable and stronger than even a hydrogen bond. Okay, so, but I wouldn't ask you to know numbers or even to do that for this. All right, so some of the vocabulary, which this is important: hydrophilic, hydrophobic, and then amphipathic. Okay, which sometimes we also talk about amphibolic. But hydrophilic literally means water-loving. So they're gonna dissolve in water. Hydrophobic usually will not dissolve in water. Amphipathic means that it has one portion of it that's hydrophobic and one portion of it that's hydrophilic. Whether or not it dissolves is going to depend upon the relative ratios and or structures, okay, of those molecules. So if we have something here, this is sodium palmitate. We can see that it has a hydrophobic. This is a carboxylate on the end here, carboxylic acid. And then this is just a large alkane. So if you put this in water, it's going to form micelles to where the hydrophobic tails will all exclude the water, and then the negative head groups will be on the outside, which is the reason, or that's how detergents work. Detergents like you use to wash your clothes and things is the fact that you put it in there, they're amphipathic, and so the hydrophobic portion of it will hopefully get in to your clothes, rip out like the oils and the grease and stuff like that. Then they form the micelles or bicelles around it, and then you can just rinse right off and go down the drain. And back in the old days, you just saw things like phosphates and stuff were just so great, because they work so well, they're so amphipathic. However, it kills off lots of things in the water stream, and so now that's why you can buy like your phosphate-free detergents and stuff like that. Okay, but yeah, this is just a vocabulary slide. Well, this is all review. Things that are hydrophilic, things that are hydrophobic. Once again, some of this, it's going to depend upon the structure or how large. So notice it says low molecular weight. That's important because if you have an alcohol or a ketone like this one, okay, I don't know that this is a ketone. It's going to be hydrophobic because the surface area, the exposed surface area is so huge that's hydrophobic that one little oxygen is not going to be enough to overwhelm it. And so that's why you have to kind of take it with a grain of salt. Now you can do things as you learn in organic chemistry to try to make it more hydrophilic or hydrophobic. We don't get to do that in vivo because we're limited. We can't all of a sudden change our ionic solvent or anything like that. Now, if you took medicinal chemistry, or if you take medicinal chemistry, and that was a drug, then we put other functional groups on it to try to make it more hydrophilic or hydrophobic. But that's for a different class. All right, we've already talked about hydrogen bonding. I'm wanting to spend more time on, and this is just showing you an example of how hydrogen bonding can affect the physical properties of the compounds. And so if we just look here, all three of these compounds have about the same molecular weight, but they have very different physical properties, and it's due to their ability to hydrogen bond. I used to always try to point this out in organic chemistry as well, like in the very beginning of Organic Chem 1, in the sense like if we look at methane, which is nonpolar, it's a gas at room temperature because the boiling point's already negative 161 degrees, whereas ammonia, I think that's supposed to be positive. It should be positive 30. Because you can have liquid ammonia, that should be a positive number. I did not make this table. But ammonia, is a liquid at room temperature. And so it can hydrogen bond, but water has an even higher degree of hydrogen bonding. And so it's at a much higher temperature before it boils to go to a gas. Okay. All right. Okay, so this is just showing you the hydrogen bond capabilities that we use in biochemistry. And if you look at the second one down, that's an example of an organic. In organic, you didn't really push it. In Gen Chem, you are given like strict rules. Like, you have to have both hydrogen bond donor and acceptor to be a true hydrogen bond. But here we don't. We talk about it being hydrogen bonding between the water and then the acyl carbon. Okay, I mean the acyl oxygen, even though it doesn't have a hydrogen hanging off of it. Whereas if you can reciprocate, typically those can be stronger. So that's one of the reasons why hydrogen bonding between two waters is so strong. Okay, because both water molecules can do hydrogen bond donating and accepting. This just shows you how it's important in vivo. Some examples, especially here. These you probably didn't get to cover as much in greater detail in organic chemistry. They do some with nitrogens, but they probably don't focus, and they do very little with sulfurs, but sulfurs do not hydrogen bond. Okay, so that's why they're not listed here. But these are important in biochemistry because they're for nucleic acids and various proteins. In next chapter, we're going to talk about this one in particular, this one right here, for protein bonds. Okay. All right, this is why I was wanting to spend a little bit more time, because it's probably been longer since you talk a lot about acids and bases. Oh no, you can do it. Maybe you can't. Stuck. Okay. You probably, in Gen Chem, you usually learn different definitions for acids and bases. You know, the one that you've learned from years and years and years ago, that acids were proton donors, bases were proton acceptors, or you may have learned that bases give off a hydroxide. That's true if it's a strong base. But what these really do, and then you learn the Lowry definitions. I'm sorry, the Lewis definitions, which actually has to do with electrons. Okay, Braun said Lowry has to do with looking at it with respect to protons. The Lewis definition has to do with respect to electrons, like something's a Lewis acid or Lewis base, and we'll go over that later on. Okay, in biochemistry, they're very important. But, strong acids, strong bases, that's the one that you probably the most familiar with. You had like hydrochloric, hydrobromic, and hydroiodic acid. In aqueous solution, they completely ionize. Strong bases, there's only a handful, those that are strong enough bases that completely ionize as well in aqueous solution. Usually in vivo, these aren't good, okay, because of the fact that they would be very, corrosive in the sense that with tissues, okay, so usually we don't see this in any great sense, okay. So we won't go there. We speak primarily of weak acids and weak bases. And here, and this was just on Jeopardy last time. And so they had something that asked like, I can't remember if it was a base that gave off a conjugate acid or the acid that gave off a conjugate base, but that was actually one of the Jeopardy questions. So I got to impress my wife with my knowledge. And so my wife and my baby son, I'm sure he was really impressed. But that's beside the point. But in a weak acid or weak base means that in aqueous environment, it doesn't completely dissociate. And so you're going to have it in both forms. Okay, so you have whatever was a hydrogen bond acceptor is the base becomes a conjugate acid on the other side, and vice versa. The acid was what gave off the proton and becomes a conjugate base. They are reversible typically, and the equilibrium can go either left or right depending upon the pKa of that environment and the functional group. Okay, so like what's that environment in? And that's one of the reasons why proteins and enzymes are successful, is that they can take things that you learn in organic chemistry that have pKa's that would not be conducive for being in vivo. However, inside that enzyme and that protein, you're in such a sequestered environment that it changes the pKa of those functional groups to where now carboxylic acid isn't nearly as acidic as what you thought it would be. Or maybe an amide or an amine is not nearly as basic as what what you thought it would be because of the environment that it is. It's not just in a test tube like you would have it in an organic lab. So that's where pKa's become very, very important. Okay, normally I take a whole lecture pretty much and we derive the Henderson-Hasselbalch equation and we derive all of this. And so now this is the answer. And I'll briefly walk through it, but we don't have enough time to do take an entire class and just going through and solving this. Because I do expect you to know the Henderson-Hasselbalch. Okay. You can either memorize it or you can learn how to write it out just based off of the definitions of an acid and base.
So this is what you want us to memorize?
No, this is just water.
Oh.
Water.
So what was the picture that
We're not there yet.
Oh, okay.
You're jumping the gun.
I know, I was like...
You're giving away the story. Like baby's mother dies. They put rocks on Schindler's grave. Titanic. It happens. Okay. All right, so here, this just shows you water. There's a special ionic. So one thing that's always a pet peeve of mine, and it's very important in biochemistry, is the letter K. You have to make sure that you clearly distinguish between capital K's and lowercase k's. Capital K's are equilibrium constants, which are thermodynamic. Okay. Lowercase k's are kinetic rate constants. Those are kinetics. Now they are related to each other, but they are not interchangeable. So that's why here we're using capital K's, because this is literally the ion product constant, or equilibrium constant for water. Ka is just the equilibrium constant for the acid. So usually you have to have some barometer or gauge. They always do it with respect to the acid and not the base. Okay, really, that way you don't have to know both Ka's and Kb's. You just have to do everything in terms of Ka's. Now you have to know Ka versus Keq, which are equilibrium constants, but we'll get to that later. So this just shows you the definition with respect to water. You know, you always have the products over the reactants. The concentration doesn't change. Remember, this is a liquid. It's not written on here. Oh, stupid thing. You know, normally they put a little L, and these would have AQs. And if you remember from Gen Chem, pure liquids and pure solids don't get included into the constant because they are effectively unchanged. And so that's why, if you look at this, the 55.5 suddenly disappears, okay? But this just shows you for the Kw under standard conditions is 1 times 10 to the minus 14, okay? So that's where we get, if it's neutral, pH 7, you're gonna have 10 to the minus 7 here and 10 to the minus 7 of that. That's where those numbers all come from. But like I said, normally we take the time to work it all out on your own. You may want to review that part in your textbook or online. Okay. Oh, whoops, let me go back. So, but weak acids and weak bases are a little different. In the sense that now we don't just have water, we have another player, which they like to use this generic HA. And so this is the conjugate base is A minus. And so they want to determine Ka's, okay? Like we're gonna do everything in terms of the acid and not the base. And we're going to look at it with respect to this equilibrium constant. Remember, equilibrium constant literally just means the products over the reactants. And to go backwards, it's going to be 1 over the other's equilibrium constant. Okay, by definition. You know, this is algebra. And so whenever we do this Ka, you're going to have H₃O plus times A minus divided by HA. Remember, the water is a liquid, and so it doesn't get included. Now, one thing... It's going to drive me nuts. Let me just change the color. We have this. What is this P? What does this P mean? What is the P? Does anyone know? Did they go over it in calculus? Or algebra? I don't know which. What is P? Negative log base 10. And so it's a function, just like addition and subtraction and all that kind of stuff. It's a function, and it literally means negative log of base 10. Okay, and so that's why you can have pH is literally negative log the concentration of H. That's supposed to be concentration of H plus. Okay, that's equal to pH. Okay, so it's just an easier way of writing things out in a function. So we can have pKa is negative log base 10 of Ka. You can have pKeq. You can have p number of students, which would be ridiculous because we don't have that many. But it's one way to take things that are either really big or really small and make them more manageable. Okay, since it's a logarithm function. Okay, so how does this why? Whoops, I got these out of order. Think that through. Keep that in mind. Okay, these are just some of I would give you this, do not memorize this, but I would give you pKa's. These are just some pKa's of common things. So you can see here a pKa of pyruvic acid, which when it looks like this, does anyone know what pyruvic acid is called whenever it's conjugate base? Pyruvate. And pyruvate is very, very important. You're going to see pyruvate a lot next semester, but this is lactate and acetate and so on and so forth. But you can see, pyruvic acid, it is acidic, whereas you could go to, you can also have more than one pKa. So if you look at malonic acid, it's got two pKa's because there are two acidic hydrogens. Okay, one of them is under acidic conditions, and one of them is at much higher higher pHs before you can lose it. Okay. But yeah, I would expect you to understand what that means. I would also expect you to be able to, if I gave you, let's just look at phosphate here, and I said pH 10. Well, what that means is essentially all of this hydrogen's gone and all of this hydrogen gone, and all of these hydrogens are still there. So this would be the predominant form of phosphoric acid at that pH. Okay. So if the pH is higher than the pKa, you've lost that hydrogen. If it's lower than the pKa, you still have that hydrogen. Okay. Remember, it's base 10. And so if you're just one pH unit off, you already lost 10. What is that? It's a factor of 10. If it's 2 pH units off, it's a factor of 100. If it's 3 pH units off, it's a factor of 1,000. So that's why I can say it's essentially gone. Because the 2.14 be a factor of 10 to the power 8. And so very, very little of that hydrogen's around. All right, so let's go back to this is Henderson-Hasselbalch. This is where you're going to have to get to where the part where, like I said, you can either memorize it or know where it comes from. And I would always take lots of time in the past to work this all out for you. But pH, usually we're given pH, or we can determine pH, and we may know the pKa of something. And so this is how they're related to each other, the relationship between them. So notice the water, a lot of times in biochemistry we don't even include it because it doesn't change, but this is the weak acid with its conjugate base. The Ka, once again, is conjugate base, which is A minus times H plus divided by HA. It's the same. Nothing has changed there. That's nothing new. So that's Ka. Put this in terms of pH, since there's an H here, and pKa, since we have a Ka. Which that makes it so much more easy for us to have numbers that make sense. Because otherwise you're talking about like 1 times 10 to the minus 14, or 1 times 10 to the power, or 1.35 times 10 to the power, 26. It doesn't make sense. Versus if we look at something that says like 14 or 0.3 or something like that. Just remember, on your own, you may want to work your way through this in the sense that whatever you do to one side, you have to do to the other side. What we can do then is we can actually substitute. And if you take the logarithm of both and you rearrange it, you're going to get this term right here. Okay, so the negative log H is equal to negative log Ka plus the log of the base over the acid form. And then this by definition is pH, and this is by definition is pKa, and so that's where this is the Henderson-Hasselbalch. Sometimes it's written this way, which is the same thing. pKa is equal to pH
minus the log of the conjugate base, which this time I'm going to be A minus over HA. It's the same thing. Because all they've done is they've subtracted that one term over. Okay, and so that's why they're identical. And as long as you know how to use this, then it's going to be a lifesaver. We do this all the time for medical preparations and also for buffers and things like that in the lab. Okay. So, what does this mean? This is the take-home message. As I mentioned, many times you can determine pH or have an idea of pH. From that, if you know pKa, you can get the relative ratio of acid to base form. Or if you know the acid to base form, you can figure out the pKa. Or if you know the other two, you can figure out the pH. Okay? But the take home here is if the pH is greater than the pKa, so that means that this number is bigger than this number, you have to realize that that conjugate base form is going to be the predominant form. That's what I did back there at that table when I said at pH 10, the thing that was pH, that had a pKa of 2, it was going to be the conjugate base form. Because the pH was so much higher than the pKa. Likewise, if the pKa is bigger than the pH, because of this relationship, that means the acid is going to be the major form. Now, if these are equal to each other, then and once again, I didn't write this, otherwise I would have done it as this is A minus over HA, because it gets to be a pain to write conjugate base in weak acid. If these equal to each other, this becomes 1. And the log base 10 of 1 is what? What is log base 10 of 1? That's 10 to what power is equal to 1? 0. So that means this entire thing is 0. And so that means that the pH and pKa are the same. And so if pH and pKa are equal, that means you have equal concentrations of the conjugate base and the acid. Okay. So, for example, let's see, how do I? No. There. All right, so let's say that we've got this. This is very important with respect to medicine. Because the pKa of the functional groups of the medical drug affect what part of your body, whether or not it's going to even be absorbed by your body, and what part of your body it's going to be absorbed into, or body. Okay? So if we just take this generic, that's why you could put a real drug there and come up with its real pKa, it's like aspirin or what have you. As long as you know that pKa, I mean, does anyone know why I took these pHs just roughly? What's approximate pH 0 to 1? Part of your body, stomach, it's really acidic, versus what part of your body is around a 5 to a 6, usually more closer to 6, usually. Well, it depends what part of it, but your intestines, right, it's going to be more, so depending on your intestines, it becomes more and more basic. And then pH 7.41 is the blood. Okay, so just giving this scenario here, what's going to be the predominant form at pH 1? Is it going to be primarily HA or A minus at pH 1? It's HA. In fact, you can figure out the exact concentration, or I should say the exact ratios based off of this, okay, and figure out. Whereas at pH 5, which one's going to be the predominant form?
Conjugate base.
The conjugate base. Okay, and at 7.41, which one's going to be the predominant form? Same thing. Now, if we're just talking about a generic drug, which form, HA or A minus, is going to be more likely to be absorbed by the tissues? Assuming that there's not a transporter specifically for it, theoretically. Is it going to be HA or A minus? HA, why?
Wasn't it difficult for ions to get through?
Exactly. Usually, and there are different, I mean, obviously if there's a transporter or if it's got a, special pore or something like that, or if it doesn't have to be internalized, like maybe it's an antihistamine which doesn't bind on the outside, then all bets are off. But if it's something you need to get it into the cell, then typically the HA form is going to be the predominant, is going to be more easily absorbed. So in this instance, most of the absorption is going to be occurring in the cell. Okay. Very little would be, or the least amount would be in the blood if you get to him or her as an IV. So that's why this is actually, and like I said, you can figure up the ratio because since we know that the definition is pH is equal to pKa plus the log of, I'm just going to say A minus over HA. You can figure up the ratio based off of just the numbers that we have here and figure up the percents. Like, you literally can. I would suggest that you know how to do that because that's always good to know. It may be on a quiz or an exam, or it's just good to know in general because what you can do here is we know pKa, it's 3.5. We know the pH. So what you're going to do is you're going to have pH minus pKa is equal to the log of this ratio. Okay, and so then you just, how do you get rid of logs? Log base 10, I should say. How do you get rid of that log? You can't just divide by log. What's the antithesis? What is the Satan to the log? Sorry, that was faith integration. It was really bad, but I have to really push it. What is the opposite function of log base 10? Pardon?
Base 10.
Yeah, it's 10. So literally what this is 10 to the power pH minus pKa is equal to A minus over HA. So you can figure up this ratio just by that right there. And so in this instance right here, we'd have 10 to the, excuse me, 1 minus 3.5 is equal to A minus over HA. So we'd have 10 to the minus 2.5, which obviously that's going to be, is equal to A minus over HA. This is going to be less, that's going to be a decimal point. Can't do it in my head. This is where I'm stuck in my head. But, and then you can literally figure out the percentage. Like, it's going to be some small number. So that means there's going to be more HA than A minus. And then you could say, if you wanted to know the percent, you have to realize that A minus plus HA has to equal 1, or 100 usually percent, right? And so therefore, if this comes out to, and I'm going to make this in rough because I don't know, maybe 60-40 or something, but because I can't do that part in my head. That's not going to be 60-40, it's going to be bigger than that. So I think I can really a lot bigger than that. So that's why Henderson-Hasselbalch is really important. Because you can literally figure up, all things considered, all things equal, like the relative absorption, the relative percentages of what form of the drug or the amino acid or the protein. Will the protein look more acidic or more basic under these conditions or in different tissues? This is just one example. Okay. All right. This is the kind of question that really is in the book so far, in the back, and you're doing Gen Chem, where you can figure out if you have so much base and so much acid, you can figure it out and figure out the pH, which we can do. This one's relatively simple. We can do one of these real quick. Let me move this. The hardest part, or I shouldn't say the hardest part, but one part that people on these real life examples can easily make a mistake at is just to figuring out which one's the A minus, which one's the HA. Okay, so how do we know if we look at this one? This is just when you need to calculate the pH. And remember, Henderson-Hasselbalch, which you're going to be hopefully memorizing. Oh, stop doing that. Is P, I'm too close to it. It's pH. No. Serenity now. Okay, is equal to pKa. Sorry about that. That's log of A minus over HA. Okay. Where is the? I'm gonna go back to the. I would have to give you the table with the pKa's. I wouldn't expect you to memorize the pKa's of all forms of phosphate. Okay, I would give you that in the table. You just have to be able to figure out which one's a which. But in this example that we have right here, which of these is A minus and which one of these is HA? Is this very first one, is this HA or A minus? It's A minus. How do we know that? Because some people, like especially when there are lots of subscripts and all this kind of stuff, it can get lost in it. How do we know that one's A minus? It still has an H. What? It has less hydrogens. Whereas this one has one more hydrogen, so it's the HA form. And so we have pH is equal to, and like I said, I'd have to give you the pKa, or I'd give you the table with pKa's in it. So it's 7.2 plus the log of literally, so whoops, see, I forgot to even write it on there. That one's A minus. This one's HA. So A minus 0.063 over 0.1. So just make sure you know how to use your calculator correctly, which I can't guarantee that I can use my cell phone calculator correctly. Come on, I know you can do it. You're supposed to, oh, not tangent. I want log. Okay, so 7.21 plus the log of, and please don't take my word for it that this is right. You want to double check my math, so I'm using a cell phone, but I'm getting 5.00. So you can eyeball, see if it makes sense. Like if the pH should be going down, going up, based off of you have more acid or more base. Since we have more acid in the base, it should be lower than the pKa. It should just make some logical sense. But yep, that's how we roll on that one. Okay. Titration curves. You can look over this on your own. You did a lot of these in Gen Chem labs, and so you know what it looks like. One thing that we will do is you will see titration curves with amino acids. So next chapter we'll actually look at some titration curves with respect to amino acids. But another thing is you can use the Henderson-Hasselbalch equation and figure out how the pH changes as you add in either acid or base, or as you start to do other reactions. The hardest part here is to figure out what changes. I actually used to do, and I didn't teach you guys any of you guys for Gen Chem 2, but I did what I learned it was called ice tables, and so I used to teach everybody what I called ice tables. Not immigration services, please. That's timely in this day and age. But no. So what I would do here is we're adding HCl, which is an acid. So we'd have our HCl. The Cl part doesn't matter so much. Plus, is the H going to react with HA or A minus? When you add in that acid, that H plus, is it going to react with A minus or HA? A minus. That's the hardest part, I think, for this. And it's going to go to form HA. Oh, so I would do, I'm going to have to make my table down here because it's going to really annoy me. No. Okay, sorry. I would do what I called ice. Oh, it's so annoying. It's supposed to be an I. Just trust me. It's an ICE. For initial concentration, the change in that equilibrium. And so for each of these, you want to convert them into, because we don't have enough time to do it today, but you want to convert them to moles, because remember it's a mole of H plus will react with a mole of A minus. So you convert it to moles. And remember, for the change, you look to see whichever number here is the smallest. Okay, so for example, here I'm just going to tell you H plus is going to be a smaller number than A minus. So the change is going to be minus the amount of H plus. That's also how much A minus is going to be decreasing. So, which I don't know, I don't have that number in my head. So let's say that this was X. You can figure it out, moles, based off of the concentration right there. And this, of course, was the initial concentration of A minus, and this is HA. Of course, you can figure up the numbers from before. We were already given those numbers. This would be minus X, and this would be plus X. So, of course, there's nothing left at equilibrium. This would be A minus X, and this would be HA plus X. Then you just put that into your equation for Henderson-Hasselbalch and plug and chug. And so if X ended up being, oh, actually I can't do this in my head. It's about 0.0001. You may want to double check that. Then, for example, then the A minus is going to be also subtracted by 0.0001, and the HA is going to be added 0.0001 to whatever that number was. Then plug and chug. Okay, the rest of this chapter really has to do with, well, it talks a little bit about buffers and osmotic pressure, which we don't do a whole lot with osmotic pressure anyway. But you can look at it on your own for the rest of the chapter. And that way, we can really focus on things that should be the newer stuff, maybe completely new to you, chapters 3 and 4 for the rest of this time. Okay.